Well, hello and welcome to our next episode of 3Din30, or sometimes, as I like to think of it, Java with geniuses. Today, we're going to be talking about how it's made Impellers. 3Din30 is Bello 3D's LinkedIn Live and YouTube Live channel. We host this about every 2 weeks. Sometimes with the holidays or with the trade shows, it can get a little erratic. So make sure you follow Bello 3D to get the latest show schedule. We're going to dive into a new topic every time. So today's pretty cool. In the metal additive manufacturing industry, turbomachinery as a category is quickly becoming the killer app. If you remember cell phones, you remember computers back in the day, there was always one app that kind of drove a lot of adoption, and that was called the killer app. And that's really what we're seeing here is a lot of companies moving in to metal additive manufacturing to get access to turbomachinery. So specifically engineers in the aerospace, as well as terrestrial energy generation, they all look to AM for faster lead times on parts. They want new innovations, things like supercritical CO2, which is at the cutting edge of energy right now. But for those not as familiar with turbomachinery, or people who just need a refresher, there's a lot of complexity around this technology, but there's also a lot of opportunity if you understand it. So how do you optimize components? How do you think about the manufacturing limits? What does AM offer today? What's it going to unlock for you tomorrow? That's our topic for today. So 3Din30, how it's made Impellers. We're going to dive into the definition of turbomachinery. We're going to look at what it's used for. We're going to talk about how to optimize the technology, which is really at the core of this, and then how to preserve the design intent of that optimization and actually manufacture it. So, and don't forget, we are live on this session. We want to hear from you. We want to hear your questions. So make sure to drop in a question during the show. Joining me today are my two geniuses from Concepts NREC. Ryan Lussier, product manager for MaxPack. This is a CAM software for programming 5-axis milling of impellers and turbomachinery. And then JB, interim VP of engineering and associate director of product for CAE, a software for design and analysis of impellers and turbomachinery. Gentlemen, how are we doing today?
Great.
Very good, Mike.
Sweet. So JB, maybe you could give us a little bit about yourself, a little bit of background.
Yeah, I studied mechanical engineering early in my career, focused on aero and hydro design. Jumped in on the manufacturing side of turbomachinery. Got to see the design intent in the manufacturing world. Bit of subtractive, bit of additive. It was great to see. And then now jump back into design software and engineering.
Yeah, it's amazing what is coming. I had an interview with a customer. He basically was saying that imagination is the only boundary right now. With what you can do in software, what you can do in manufacturing, it's just that whole rethinking process is really where we are, which I think is powerful.
Absolutely.
So, Ryan, a little bit about you. What are you up to?
Well, lately I've been chasing down user feedback to help improve our CAM software MaxPack here at Concepts NREC. But before I joined the team here, spent about 9 years in the manufacturing of turbo components. So working on anything from impellers to turbine blades, and worked both in subtractive and additive worlds there.
Mostly rotational or static as well?
A little of both. Yep. So we did rotating components like blisks and also stators for jet engines as well.
Nice. I always respect the difference between a blisk and a stator.
Nice. Appreciate that.
Yeah. I remember the day I had to learn that one. It was a fun conversation. So, Ryan, a little bit about Concepts NREC. What does Concepts do?
Yeah, Concepts NREC is a multidisciplinary company with a strong specialty in turbomachinery. Been around for, I think it's 60 years now, and we're really viewed as the experts in the field. And we can help at any step in the product lifecycle. We have a really strong design team, engineering team that can help you realize concepts or tailor things to this particular application, in-house manufacturing to actually then go produce those components so you can actually realize your design. And we've also been taking our knowledge from the last 6 decades and packaging it in our software, both on the CAE design side, so that you can become an expert yourself in design, and also on the manufacturing side with our CAM software.
Yeah. So when we were mentioning that design intent, like preserving design intent, that sounds like kind of everything in that contained package there.
Yeah, and actually, we have a pretty good system that lets you jump between the two. We call it Agile. So it really helps you go right from design right into manufacturing. And but in a nutshell, basically, if you have a turbo machinery problem, we can help you solve it.
Nice. Awesome. Yep. Solving complex problems. I've definitely heard that a lot. So let's get into turbomachinery a little bit and kind of step down. And JB, I know you're really familiar with this. Can you give us just a really high level view? What is turbomachinery?
Yeah, so turbomachinery it's specialized, but there's a wide range, right? And so what we focus on is move-in blade rows, if we can focus on that part. So it's segmented into two major areas. You either extract the energy from the fluid, okay, so a turbine, or you add the energy to the fluid, so either a compressor or a pump. And so that, fluid, if it's a gas, you're looking at a fan, blower, or compressor. If it's a liquid, you're looking at a pump, okay? Now, okay, fan, blower, compressor, let's talk about those a little bit. Maybe it's high level, so maybe I'll think about more from a household perspective. So fan,
I'll help you out here.
There you go. So yeah, fan. You got your household fan here. I've got old English sheepdogs, and they love that fan blowing on them. If you look at this, high air, high flow, low pressure. So it's the pressure rise from the inlet to the exit. It's going to be fairly low, like a pressure ratio 1.1, right? A blower, if you think about, you have to overcome your ducting system. There's resistance in there. So it's going to require a little bit more pressure versus a fan where it's got to get through that enclosure. So that's the blower. High volume of air with a little bit more pressure. Now a compressor, it's going to be even more pressure. Let's think of a turbocharger, right? So it's going to be greater than 1.2, let's say 3.5 for pressure ratio. And some, say it's lower flows, but some compressors do need higher flows, right? So, and then if it's a pump, you're looking at head rise. Best image is probably the height of a fountain, right? That's the head rise you're put into the liquid.
Nice. And, we actually do have a question already coming in. This is coming in from Michael, and he's asking, does your company's software include the software to perform FEA analysis?
Yeah, I mean, we definitely do have that option. Jonathan's probably better to talk about that from the CA side of things, but you want to talk to that, Jonathan?
Yeah, so aerodynamic analysis, obviously the CFD side needs to be coupled with the mechanical analysis, and we understand that the geometry is very, very specialized versus a general CAM. So we provide that input that basically boundary conditions needed to be able to mesh and perform an FEA analysis. So absolutely.
Nice. Very cool. So we were talking a little bit about turbomachinery and kind of breaking into the different concepts there. We had the dog and the fan. So Ryan, like in the real world, what are you looking to turbomachinery to accomplish, like functionally?
Like Jonathan said, it's really all about energy conversion, whether it's extracting energy from fluid or adding energy to a fluid from a mechanical or electrical source. So yeah, that's really what it's all about. So different applications, like we've talked about, fans, like you brought a great picture of the dog. That's a good example of an axial component where you're not really changing the predominant direction of the flow, and you really are focused on flow, right? So you see how much flow is coming through. The dog's hair is blowing all over the place. And then you have other applications that are more pump related. JP mentioned fountains, but you also can see them in your pool and things like that. And those are more about driving pressure to overcome losses in the system or to, meet the requirements of your application.
So some different categories, it sounds like, and you kind of mentioned the.
And there's also actually something called mixed flow too, which is somewhere in between the two, where rather than having a sort of 90-degree change in direction like you would in a radial component, you're more around 45 degrees.
So you got kind of your radial, which is your 90-degree, you got your mixed, and then you got your axial, which is basically kind of the fan idea.
Yeah, exactly.
Okay. And you did already mention a couple real world examples. You mentioned like pool pump. We showed the fan. What are some other things that somebody might find in their home for real world examples?
Good question. I mean, I think maybe not in your home, but one of the most obvious ones is the turbocharger in your car, right? I think a lot of people take advantage of those, which is actually, turbine and a compressor coupled together typically. So yeah, I think that's one that a lot of people can associate with. You get that little boost sound. that's coming from your turbocharger, and really takes advantage of otherwise potentially wasted energy and helps make the engine more efficient.
And in that case, you've got kind of both things going on. Like what you mentioned, you got sort of you're taking energy out of the fluid and you're putting energy into the fluid on the other end of it.
Yeah, sort of. You're definitely harnessing energy from the fluid, and then on the other end, using that to take advantage of like increasing the density of your fluid to be able to have a more efficient combustion process.
Nice. So, I mean, we look at these technologies, and where we have a lot of conversations is when design engineers are trying to optimize around something, right? They're really trying to drive the needle forward. And JB, I know you work on the design side of things. What would an engineer look to try and optimize turbomachinery, or maybe more specifically, like an impeller?
Yeah. So historically, if you look at the way these evolved, I mean, they started as fairly simple shapes, fairly simple geometries. But let's face it, today's world demands high efficiency, low energy use, high performance, and that's where we come into the optimization side. So if you think about some of the items that we mentioned, there's a pretty high operational life. They run most of the day, right? Mm-hmm. So it makes a big impact on your energy use if you do it properly. So if you think about that design, I think you have an example.
Yep.
Yeah. Okay. So this is one of your turbo pumps. So you see this 2D contour that comes through. Obviously you got a very, very high focus on slopes and curvatures, and then number of blades, the thickness of those blades from inlet to exit. Let's say the blade angles on the inlet and exit in relation to the RPM and the flow, right? But also throughout as you go from that to wrap from that axial all the way to the radial. And then you're managing velocities throughout, you're managing total pressures that convert to static pressures and things that you're trying to avoid, like aerodynamic blockage as it goes around the leading edge or throughout this passage, as well as recirculating flows.
And now we've got, when I think of optimization, it's not maximization, right? So you're not just trying to shove as much as you can. There's always a downside to doing too much or too little. What's the downside with doing too much?
Yeah, so that case that you showed is really interesting. Ryan talked about different geometries like axial versus radial, where in that pump example, you literally have two sections of focus. The first focus is the inlet, right? If we bring a picture up, so it's what I'd call an inducer, right? So there's if you think about this is rotated at very, very high RPMs, and depending on the arrangement of the pressures at the inlets, there's a certain amount of suction that happens, okay? And what happens is if you allow that liquid pressure to start to drop, right, below vapor pressure, bubbles start to form, right? You have this cavitation effect, okay? And the challenge with cavitation, like you're designing it to pump liquid, not gas, right? So what happens is you start to lose head rise, you start to lose efficiency. It can actually even damage your blades, right? As it sort of bursts on that vein. So really the focus is slowly increase the pressure through that axial portion, and then the radial portion can do all the work for the head rise, if that makes sense.
Yeah, and so I mean, we kind of have, this is one of our graphs here. Maybe you could walk us through sort of what's happening.
Yeah. I mean, you're hoping to stay in that liquid phase, right? And if during the inducer portion, if that as you do the work, if it's too rapid, the velocity gets up and the static pressure drops to that gaseous phase, and that's what you see.
And that's what, like those air bubbles.
Exactly.
You might see in those slow motion videos. Okay.
Yeah.
That makes sense. So we have had a couple questions here. I'm going to take a little break and take some questions from the audience. There's one more for Bello here. Somebody's asking about our XC platform. So we have a system called the Sapphire XC. If you're not familiar with that, it is a large format metal 3D printer. It is 600 millimeters in diameter and 550 millimeters in Z height. And it is super fast. I've seen this thing print. It's amazing. 8 lasers going on all simultaneously. Very fast recoder times. It's awesome. So we do have a question here. How long is it taking to build these? So we shipped our first one right before the end of last year. So that was kind of our commitment to our customers, get the first one out the door. And we are ramping up production as quickly as we can in 2022 to get those out the door as well. If you're really interested, you'll basically have to get a quote from one of our salespeople to know what the delivery time is. But our pipeline's filling up fast. So if you are interested, definitely getting the queue on an XC. So there's another question here. Do you work with compressor fans such as CFM LEAP engines or jet engines for aerospace applications to make them more fuel efficient specifically? This is another question from Michael.
Yeah, so I see it's mentioned a specific engine. I mean, I can talk about engines in general. Yeah, absolutely. From a gas turbine side, our software is very applicable to that type of engine arrangement and those types of blade shapes.
And the same thing on the cam side. We work with that kind of the shapes that those designs produce all the time. That produce some of the best tool paths in the industry.
Yeah.
And there's another question here. Does the software include simulation of operation?
It's a great question. It does. We can handle both material removal simulation, so basically simulating the actual amount of material removed and the residual shape of that, and also machine simulation, where you're actually looking at your machine tool and the motion it makes.
Okay, nice. And please feel free to keep bringing questions in. We are obviously live. We're going to take your questions as soon as we can. We love to hear from you on the show. We love to get to our speakers, and you can almost think of this as an Ask Me Anything. With a little bit of a narration going on in the background, so you can kind of tune in and hear what all of this is about. So want to shift gears a little bit. We talked about the design side, and I think we went through pretty much everything there. Now kind of looking at the manufacturing side. So you've got these complex parts. JB's gone and designed it to be fully optimized. He's eliminated cavitation in theory. and now Ryan, it's kind of going to go to your side of the fence here to manufacture this. What are some of the things that you think about? What are some of the challenges that you look at in manufacturing these parts?
Yeah, I kind of break things down into two predominant types of challenges. You have geometry challenges, and you have sort of surface quality challenges, and that can be related to like actual surface roughness, or some people might say surface finish, which is predominantly and traditionally driven by the step over your tool. And on the geometry side, it's more about, okay, so Jonathan's made this great design that's really efficient, but now maybe you have some blades that are kind of close together or curved over in a funny direction, or you have an intricately shrouded component, and now you have a lot of concerns about tool access. And so there's the challenge of what orientation you could come at the part with your tool, and we do that automatically. We've built in some algorithms to kind of calculate the best way to do that. And on the more surface roughness side, the way we solve that is all about giving you control over the path the tool takes and the step over as well. And yeah, so.
Yeah, you mentioned step over a couple of times, just in case somebody's not familiar with the terminology. I know you kind of shared this graphic with us. If you could walk us through sort of what this is and what's happening here.
Yeah, I mean, step over, it's essentially just what you see between the yellow lines there. So in the subtractive world, you have to go through and essentially pick away at the surface. So each time you take a step over, assuming you have like a spherical tool, you end up with a little cusp height. Kind of imagine it like when you take bites out of a sandwich and kind of the shapes that's left afterwards, you have these little cusps. So yeah, and that affects your overall roughness of the surface.
I'm thinking of Bugs Bunny for some reason, and there's always like these little indentations when one of the cartoon guys takes a bite.
Exactly.
So we have a question here from Roberto, and he's kind of referencing MaxPack has the ability to aid in the subtractive manufacture of one-piece shrouded impellers. Has Concepts NREC looked at any performance differences between subtractive and additively manufactured impellers? which I think is a great way to kind of segue into our next little area.
Yeah, I mean, I'm not sure if in terms of performance difference, are they talking about more the actual mechanical performance or performance from like the CAM software side or the actual manufacturing process?
I would think, let's just assume it's after it's manufactured, real world performance potentially.
Yeah, I mean, whether you make things additively or subtractively, one of the things, like I mentioned, surface roughness, well, that's a challenge for both of both those applications, right? So on the additive side, right off the machine, a lot of times you have a pretty rough surface, so you have to go through and post process those either with some kind of abrasive flow technology, or sometimes people will actually go through and pair subtractive manufacturing with additive manufacturing to get the desired surface roughness. You can the printed surface will have imperfections that you have to remove. So maybe there's some minimum amount, half a millimeter or something, that you have to remove to remove all those surface defects. So I think at the end of the day, once you've achieved those desired performance, those desired design characteristics, I don't think you really will notice too much performance difference. Although I think it really comes down at that level, probably more comes down to mechanical properties of the material in terms of how far you can actually push that component.
I know just from working on some of the case studies that we've had, at least for some of the public applications, there's been like this time to market aspect. The performance aspect it's just sort of what's on the drawing. I don't know that people have looked at it from hey, we're going to outperform traditionally machined parts necessarily.
Yeah, I think if you're really focusing on performance and manufacturing and pairing design too, like you really have to take advantage of the complexity aspect of additive manufacturing, where you can add new types of features that you couldn't otherwise. Things that you can't machine subtractively, like small holes, whether you're using it for cooling or controlling flow. I think that's where you really can realize performance gains when you start to get creative with your designs.
Yeah, if I can add, I mean, there's
Please.
some designs where you can't actually get the tool into a shrouded impeller because of the shape, the angle, and you have to obviously braze a shroud or something on top of it. So that's one other option. But if you're like for like on the leading edge shape and the blade angles, right, aerodynamically it should have the same performance. Mechanically, I don't know. That's a different. It depends on the mechanical properties. So.
Yeah, the testing I've seen, guys are meeting their targets. I really don't know enough about it to say whether that's exceeding what's been machined or not, but they're having targets and they're able to meet them with additive manufacturing in terms of the material composition, in terms of the geometries, like what you're saying. They're getting the performance, they're getting the pressure rise out of it. So we have a couple of case studies on impellers, and I'm going to drop some links in the comments here once we get off the live session. If you're interested in learning about some of the performance measurements that have been done on for aerospace and for energy, we'll provide both of those in there, and you can kind of dive into that if you want. So, now that we're sort of on the additive manufacturing, right? Actually, you mentioned service finish. We weren't done with service finish. So, we kind of talked about challenges of both machining and additive, and there's some things that you brought up around service finish. Why are we so focused there? What are we trying to optimize around service finish, and what's the downside?
Yeah, I mean, so there's a few different things that it can impact the formation of your boundary layer on the airfoil. It can prevent laminar flow from forming, which will destroy the performance, and can also have structural issues too, right? So there's definitely a correlation between like fatigue failure and having small imperfections, or I mean that you can have that on both the subtractive or additive side, right? If you have certain mismatches or like undercut subtractively, that can cause issues in high cycle fatigue, and also if you have little imperfections in your surface that are residual from the base additive process too, those can also cause those issues.
Yeah, JB, anything to add on the surface finish side of things?
No, that's great. Nice work.
Okay. Yeah, one of the things I was heard from some of the industries is these impellers can be used in air application, like you mentioned, the turbocharger for your car, they can also be in fluids, and they can also be in highly viscous fluids, and like oil and gas and that kind of thing. Do you see a lot of impellers after they've been used for a while? Do they degrade over time? I mean, obviously it depends, but what's like some of the worst case things that you've seen?
You're saying an impeller in action?
Yeah, an impeller in action, like in a really highly corrosive environment, or maybe oil and gas environment, or somewhere where it's highly viscous.
Yeah. I mean, absolutely. You're going to see whether it's in a fluid or a gas, in extreme environments, depends on the temperature. Yeah, there's definitely cases where you're going to see let's say, attachment to the geometry, like actual. You're not going to see the nice machining marks that Ryan showed earlier. It's going to show some level of I don't know what the term is, but staining, let's call it. So.
Nice. Ryan, I did want to jump back here. We did find a graphic for you, kind of just talking about the synergy between the additive and machining. Like what you mentioned, this is not what a part looks like when it comes out of a printer. This is a part that's been printed, and then it's been post-processed, because that's what the customer required of it. So
yeah, I think one thing, Jonathan spoke to brazing too, and I think one thing that can be strong about the additive world is if you're able to avoid having to do braze by using an additive process that you compare with either abrasive or subtractive post-processing, then it can actually give you a better like yield. So you're not having failures due to cracking at the braze joint and things like that. So that can be another way to really get a big win out of combining additive and traditional manufacturing processes.
Yeah, I know we kind of talked about some of the advantages of additive. I know you guys have seen both sides of it. What are some of the challenges that engineers should be aware of if they're moving to additive or examining it?
Some of the challenges, I mean, I think we spoke to a lot of them really already. It's there's the process related things of actually making your 3D build and actually getting it to be successful. I will say that the Velo process solves a lot of challenges you might have had that are support related in the build process, but this still can be a challenge. And then also once you finally solve that, like you're kind of only halfway there, if that, where you have to then, okay, so how do we take this sort of input geometry, this stock almost, and how do we make that into a finished component?
Yeah,
so yeah, I guess what I would say is don't forget about the rest, right? Once you've built the part, that's you've hit a big accomplishment, but there's a lot more steps in the process to realize, whether it's thermal processing or like hip or solution heat treatment, or then post processing to meet surface finishes, or subtractive machining to form structural or mechanical components so they can actually interface with the rest of your machine.
Yeah, and we do have a couple questions. I did want to jump back here and make sure we get these. So how long is the typical lifespan of an impeller? That was one part, and then additive can only make small ones. I'll talk to that one in a minute.
Yeah, you're gonna love the answer. It depends, right?
Yeah, I know.
So, I mean, ideally, as processes mature, things like high cycle fatigue could be the item that determines the life, right? To make that predictable is the goal, right? I'm not going to commit to a lifespan of an impeller, but we want the high cycle fatigue to be predictable.
Yeah, and I'll jump on the second one. Additive can only make small ones. I don't know how you define small. Our printer right now, a Sapphire XC, could do 600 millimeters in diameter. And we have an impeller currently printing, I think right now, actually, that is just about 550 millimeters. So would you consider that medium in the world of impellers, or would that be considered large? I look at it, this thing's enormous to me, but 450 pounds, I think, is what the estimate was when it's done printing.
Wow.
Yeah, it's not only wide, it's actually pretty tall too.
Wow.
It's not one that I'm going to carry at a trade show, that's for sure. Yeah, that one's printing now. How big can these get?
Yeah, a couple meters, right?
Yeah.
We'll get there. Probably not in 2022. If you need up to 600 millimeters, we can help you out with that. So I'm going to take a couple look here. I think we talked. Robert had a question here on surface finish and back pressure. I think we talked about that. And then there's another question about residual stresses. Is there any research that could prove the residual stresses are in an allowable range? Not sure the context there.
I think they're probably talking about residual stresses from the build, but
yeah,
I don't know.
Yeah. Let's assume that's it.
That, yeah.
Yeah, I think there should be research on all the post-processing as well, right? At the build, depend on the direction of the geometry, heat treat, that sort of thing. I think it should be absolutely.
Definitely material dependent. If you're printing in titanium, one of the things that you'll learn about titanium is it prints fairly brittle. You're going to want to heat treat that in terms of stress relief or whatever you're going to do before you even cut it off the build plate, for example. We are working on MPDS for our Inconel 718. And once we're done with that, we're going to roll that out to other metals. So you're going to have design allowables for these metals. And in those cases, we do have specified heat treatments for what you want to accomplish on there. So I know our team's kind of working on that. It's another one of those, it depends. Yeah. We should just have a slide that says it depends. And just kind of come back to that. Let's see here. This is a good one to kind of end up on. Where do you see your software taking us into the future when it comes to emerging technologies? And we'll just leave that open-ended, and we'll wrap that up. We'll do that for both of you. Where do you see the software and in the manufacturing industry going in the future?
Yeah, there's a continued need even in those applications for cooling. Fuel cells, energy storage, supercritical carbon dioxide, right? Hydrogen, right? All of those things are areas that we're working in. So
nice, Ryan.
Yeah, I mean, I think as Jonathan said, there's still in EV you still have things like water pumps for cooling and things, and so we'll still be focusing heavily on turbomachinery, but we're also looking on starting to look at ways to diversify. We really know what we're doing with turbomachinery, but you can take a lot of what what you've learned from the challenges of vectoring tools and tool orientation and apply those in a lot of other geometries. So that's something we're looking at going forward as well.
Yeah, I'd say, from the 3D printing side, it didn't start like this, but it's kind of shoring up like this, is where a lot of the parts that we're seeing and printing, the principles used to design those parts are sort of rooted in traditional manufacturing, and they've stretched a little bit, but they haven't really gone into digital foam and these crazy things that you see really at trade shows or research papers. So I would assume that some of that starts to play a bigger role in actual production, and you get things that, because of the design freedom, you actually get that incorporated and more into parts going forward, and really having that flip the record over, so to speak, and just opening up the design window completely in terms of performance optimization. And I know, JB, you've got something for us in the oven. We won't spoil anything, but we'll see. Maybe we'll come back to that in a couple of months.
Yeah, sounds great.
Yeah, and talk about that one. I do have a question here. How long is it taking to build? So the prints on the Velo Sapphire do take days to build. This is a process. It's not done in a couple hours. It is done in a couple days. So, just kind of keep that in mind and give you a scale there. But thank you all for joining. Audience, you were great. I love the questions. I love that we're getting those questions in like right away. JB and Ryan, thank you. You're awesome on the show. And we'll look forward to seeing everybody in about 2 weeks on another session. So thank you.
Thank you.